Now let's look at sizing a typical weld. And it actually might be interesting for you to note here that the weld strength is actually higher than the strength required for most wide flange sections. And so if you have a weld like the one above, you can see here I called out for a CJP weld. CJP stands for complete joint penetration. And so what that means is that the weld will have the same thickness as the beam flange. It will be a complete penetration through this beam flange. And so, since this complete joint penetration matches the thickness of the beam flange, it's actually the weld that has more strength than the beam flange. And if this connection were to have any issues, they would occur in the beam rather than at the welds. So, moving on. To calculate weld capacity, in addition to knowing the weld strength, which you can see here is 70 kips per square inch, we also need to know about the dimensions of the weld. Specifically, we need to know the thickness of the weld and the length of the weld. Once we have all three of these variables defined, the remainder of this equation simply safety factors. So we apply a safety factor to the weld strength, reducing it by 40%, and then after that is done, and we have our full weld capacity, we then apply an additional safety factor to the entire thing, reducing it by another 25%. So there's one more number in here. I'll change the color. That isn't a safety factor, but it's still in our equation. So what is that number? Well, that number is actually what we refer to as the throat dimension. So when we're sizing welds, it's not the thickness of the weld that actually goes into the equation, it's this throat dimension. And that throat dimension is equal to 0.707 times the thickness of the weld. And we derive that 0.707 from geometry. So you can see here that if we take out this triangle and draw it separately over here, x is our throat dimension that we're solving for, and the thickness of the weld is actually now the hypotenuse of this triangle. So we can easily solve for the throat dimension is equal to 0.707 times the thickness of the weld. So bringing that all back to our equation, here's the 0.707. So if we take a weld that is 1/16 of an inch and has a length of 1 inch, and again we're using a weld strength of 70 ksi, we can simplify this equation to 1.392 kips. So what that means is that for every 1 inch long and 1/16 inch thick weld, we get 1.32 kips of capacity. If we have a 2 inch long weld that is 1/16 inch thick, we would simply multiply this number by 2. Or, if it were 1 inch long and 1/8 inch thick, again we would multiply this number by 2. So this number becomes very useful, because we can take it and apply it to many different scenarios. Rather than writing out this equation every single time, we can simply remember 1.392 per 1/16 inch of thickness per 1 inch of length. So let's now use this number to solve an example from the ARE. This question states, the beam shown has a reaction of 80 kips. It is attached to the column by an end plate welded to the beam and bolted to the column flange. How many inches of 1/4 inch fillet weld are required on each side of the beam? And it's telling us to use E70XX electrodes. And you can see I've crossed out this last piece at the end, and that's because this question comes from a pretty old textbook that used ASD, allowable stress design, and steel, as we talked about previously, now follows LRFD, or load and resistance factor design. So we are going to solve this question using LRFD. So the thickness of this weld we know is 1/4 inch. What we're solving for is the length of the weld. And lastly, we know the capacity of the weld must meet or exceed 80 kips. Now, taking what we learned above, our weld capacity is 1.392 kips per 1/16 of an inch per 1 inch of length times, here is where we place our thickness of our weld, and it's important to remember that we defined this 1.392 in 1/16 of an inch, and of course 1/4 of an inch is equal to 4/16 of an inch. So we multiply this number by 4. Next we have the length of our weld, and the length is going to be the length on one side. But of course the weld symbol is showing that we will apply a weld on both sides. And so we can multiply our length of weld by 2. This must be greater than or equal to 80 kips. Now solving for our length of weld, we get 80 kips divided by 1.392 kips per 1/16 of an inch of thickness per inch of length times 4 times 2. And we get 7.2 inches, which we will round up to a whole number, 8 inches. So using LRFD, the answer will be A. If you take the ASD approach, you will find that the answer will be slightly higher with B. But for every steel question going forward, we will use LRFD. Next we have another ARE example which asks, the weld symbol shown indicates, and we must define what this weld symbol means. So the first thing to note about this symbol is that it is a field weld. So we can scan our answers and eliminate anything that don't mention anything about field welding. So answer C is incorrect, and that's all that we can eliminate so far. Next we have these numbers, which indicate the length of the weld and the spacing, 12 inches on center. So we can scan our answers again, and we can see that we can eliminate D, because these two numbers have nothing to do with the type of electrodes. Next we have the symbol, and it is a fillet weld symbol, not to be confused, of course, with a bevel symbol, which would go the opposite way. And so we can eliminate answer A. So our answer here is B, a 1/4 inch intermittent fillet weld to be made in the field. So to wrap up this topic on structural steel details, I wanted to bring it back to these two details that I showed at the beginning of the video. And I want to look at the architectural priorities for this detail and the structural priorities, and how it resulted in a mismatch and ultimately generated an RFI on the project. Of course, the ultimate goal of this is to educate you so that you can potentially avoid some of these similar types of scenarios on future projects. The architectural industry has vast amounts of information and resources that stretch back for years and years and years, and yet often we make some of the same exact mistakes on projects because we don't take the time to look and reflect back on our lessons learned from previous projects. So I wanted to take this opportunity to discuss this particular detail. So this detail occurred at a roof where we had a louver that allowed for outdoor air intake. And basically what it looked like was a little chimney sitting on top of the roof. So it was this boxed out structure that sat on top of the roof, and here on the right you can see that the framing underneath was rather simple. We simply framed out this box and left an opening for the ductwork to move up into the chimney. Now the tricky part with this scenario is, of course, how do you support the brick that's around this chimney? So as you can see from the detail, this was, of course, a steel building. And let's start with the architectural priorities for this detail. First and foremost, the architects were concerned with weatherproofing this chimney. And so they designed flashing for water that gets inside the cavity here to be able to have a path back out. And that flashing needed to occur above the insulation. So you can imagine if they tried to flash down below here, it would not work because the water would run into the insulation, and we don't want water inside our insulation. So that flashing had to be kept high. So in order to do that, in this architectural detail, you can see that the architect placed these blocks of CMU. And they did this not simply arbitrarily, but because we had CMU backup used elsewhere on the project. However, from a structural perspective, the issue with placing CMU here is, of course, that there is no structure below it. So, the dead weight of this brick and the dead weight of this CMU is currently sitting on this roof deck. And we're relying on the roof deck to carry this dead weight over to this beam. As I've mentioned before, all loads need a path to the foundation. And currently, in this architectural detail, that load path is not adequate. This deck is not designed to support a large point load like this. So moving over to the structural side of things, the priority is simple load path, as we've mentioned previously. Simplifying the load path creates a more efficient structure. Now from a structural standpoint, this is not exactly a simple load path that we've created. The structural engineer would prefer if we could bring the brick down and simply have some type of bent plate that's welded onto this beam and potentially an outrigger underneath. That would be a much, much simpler detail than what we've created here. However, we have to keep in mind what we mentioned previously, that that brick needs to terminate above our layer of insulation. And so, both disciplines need to coordinate with one another and determine what is going to support this brick. And ultimately, what was decided upon is what is shown on the right. So we have this post up from the beam that is welded on 4 sides with a fillet weld. And you'll note here that we did not decide to weld around. And the reason for that is because if I draw a section looking down, so this is actually a plan view where we see the flanges of the beam and the web in between. And then the shape of our HSS, as I've drawn before, it's square in shape, but it has these curved corners. And as I mentioned previously, curving around a weld can be difficult. So if we were to weld all around, that would mean that they would have to weld those rounded edges, which can be tricky. So instead, we simply weld along the 4 straight sides and leave out those curved corners. Then as we move up the structure, you can see that we have this angle with one leg that comes out of the page, and that is welded on both sides to the post. And that weld is done in the shop. So this beam actually would arrive with the post welded onto it and the angle sticking out. And so this elevation needed to be coordinated. So the contractor would need to refer to the architectural detail in order to get that elevation so that they could size this post and place the angle in the proper location. Then, once that all arrives on site, there is the continuous relieving angle that is field welded, again with a fillet weld on both sides, to our angle that connects to the post. And ultimately, that is what is supporting our brick. So ultimately, structural detailing is a balancing act of accomplishing the needs of the architecture while providing a somewhat simple load path for an efficient structure and something that is relatively easy to erect in the field. So that wraps up our structural steel detailing lesson, and next we will be jumping into concrete.